Hello everyone. Today we'll be discussing Codechef Starters 92. We'll take a look at the first five problems of the division 1. Let's move to the first problem, which is rectangular tiling. So when I was giving the contest, I didn't understand the problem. I didn't understand the problem at all. I just looked at the samples, and you can figure out the pattern very easily from these samples. So let's read the problem statement. We have a rectangular floor with R with width W and length L. Okay. Now we want to tile this floor with rectangular tiles, some rectangular tiles, but you want to tile it in such a way such that the width and height of each tile is a positive integer, and it has a parameter which is not divisible by 4. So for a rectangular tile, the parameter is 2 into L plus B, and modulo 4 is not equals to 0. We can take out the 2 common. We can say L plus B modulo 2 is not equals to 0. That is L plus B equals to odd. Okay. So uh, okay. So when it is okay, let's assume some floor. Okay, let's this be a floor with width W comma L. Okay, if both are even, we can just take a whole tile which can floor this. Okay, so its parameter would be even. Let's say one is odd and one is even. Then okay, in this case the parameter is not divisible by 4 in odd even. I'm sorry about the last case. In the just even, okay, we can just divide into two separate tiles. Since both are even, uh, we can just divide. If this still remains even, we can further divide until one of it is odd and the second one is even, because we are not changing one. Okay, in case of odd comma even, if a length is odd and width is even, we can just use one single whole tile. And there is one more case which is both are odd, in which we can not find any possible solution. No matter how we divide it, will still remain with something odd, comma odd. Okay, so if there is only one edge case in which both are odd, its implementation was pretty simple. Okay, just both are not odd. If L percent 2 and W percent 2, then answer is no, otherwise answer is yes. Okay, uh, now let's go to the second problem, which is the distance coloring. Okay, in which this we are given n stones in a row and we have k different colors. Okay, and we can color this n stone with any of these a colors such that, okay, if the difference of the two indices, two stones, is less than k, then they cannot have the same color. Okay, let's say I used k color first. Okay, 1 2 3 tilde k color. Now I want to color this stone, but let's call this index j, and there is some index I. Okay, I want to color it with index I, and we are given, okay, j minus I is greater than equals to k. Okay, so I is less than equals only greater than, okay, I is less than equals to k minus j, but since this j is k plus 1, okay, j is k plus 1, we can only color it with index 1. Okay, by solving the equation. Okay, so if we have painted like 1 2 3 4 5 6, it will be 1. Now I want to color it with 2. Okay, the minimum index it requires is 1 or 2. I can color it with 1 or 2, but 1 already occurred there. We can only color it with 2, and you will see the pattern. If we color it with 1 2 3 4 5 6 7 8k, we'll have to repeat, this pattern always. Okay, Uh, so it is the general case. If n is greater than k, then it is very easy. We'll just have to choose the initial order, and then it will keep repeating. Okay. So how to find the initial order? There are k ways to color the first, because there are k colors, but we can't use this in the second. So k minus 1, k into k minus 1, till we reach 1. Okay. But suppose they are less than, there suppose they are less than uh, k colors, n is less than k, still the answer would be pretty same, much same. K for the first, k minus 1 to the second, till k minus n plus 1 for the last. Simple enough. We can just multiply these and take modulo. That would be the answer. Okay. um, the implementation for this one was simple as well. Just take the input and uh, we, I just multiplied it with counter, which is initially k, and I am reducing it until we reach 1, that is or we reach the end of the stones, which is I less than n, and until repetition occurs, which is I less than k, and then just outputting answer. Okay. The third problem is beautification of the array. Okay. So what we are given is, okay, we are given an array, and the beauty of the array is defined as summation of ai aj over all pairs. That is, we multiply every ai with every aj. Okay. Every number in the array has to be multiplied with every other number. So when we look at this, first what I did is just sort the array, because the pairwise product won't change. Okay. It seems easy for convenience. Let's say we have 1 here, 3, 4 and 7. Okay. We call this the sum. Okay. The sum of this is sum. Okay. Now if I will choose the case in which we are increasing the lower number as well as the higher number. Okay. If I increase 1 to 2, okay, so all the number, the sum, what will be the increase in answer? 1 into this will 3 4 5. So what will be increase? 1 into sum minus 1. For 3, will multiplying be 3 by 1, 4 and 7. So 1 into sum minus 3. Okay. 1 is the increment in 3, 3 to 4. Okay. Just simple. So what you can see is, we'll always need to increase the lower number. Okay. Once I discovered this, what I did is, okay, till each index I, okay, let's say 0 1 2 3 4 5 6 and 7. I went to each index and checked if I can make all the previous number in the array, like ai, equal to this number. Okay. Not the index, a1. Okay. I found out, then I found out how many I can do equal. Let's say I can do equal this one, but I must still have some like k. I might still have some operations left. Okay. I might have some k left. So then I'm distributing this equally over all these numbers. Okay. Then just computing the pairwise product. That would be simple. Okay. Uh, so let's see the implementation for this. I used module inverse. It is not actually needed. I just computed some both ways, ai into aj and aj into ai, so I had to divide by 2. Just why I use this module inverse. You don't actually need it. Okay. uh, I take the input, then sum, then add it all the numbers and sort all the numbers. Okay. Fine. Fs means final sum, where I store the final sum, initial sum, and then we'll add increase k numbers. Okay. In last, I just stored the last element when I am iterating from I equals to 1 to I less than n. Then okay, index is the number till which I can make all the elements of the array equal. Okay. So to make equal, okay, how I am doing, I am subtracting k at each index I am going. Okay, so what I am doing is I am subtracting k every time. Okay. And index plus plus. Okay, now
It's very simple. Okay, I elements have come before it, and the difference between the current and the last is ai minus a I minus 1. So this much k we have to subtract. After that, I just uh, put ai equals to ai plus 1. Okay, prefix equal. Okay, I made all ai previous to ind equal to ind. Okay, after that I just calculated the extra I will have left k by ind and some few extra ones which will not be equally distributed over all ai. I called them ext2, then distributed them accordingly, and then just calculated pairwise sum. I use modular inverse, I told you, because I calculated it twice, so I had to divide by 2. That's why. Okay, so now let's move on to the next problem, which is dividing into groups. Uh, a very standard uh, binary search problem. For me, many people use it in some other techniques such as prefix sum after the sort. Not too problematic. So what I am doing is, okay, we are given an n boxes, and in each of n boxes there are ai candies. Okay, which have the same color. Okay, so now we can we have to make groups of these candies. Okay, in each group we have to put exactly k candies, and okay, and all k candies must have different colors. Okay, so what I did is I used binary search of how many groups can I make, binary search on answer basically. So how do I check it? Main problem is the checking on binary search on answer. So how I'm checking is, okay, for each element ai, okay, let t be the number of boxes. Okay, if this ai is greater than t, I can put it in each of the t boxes. Okay, so the number of candies I can use is candies plus equals to t. Okay, for each ai, and if it is less than t, I can put all of them in different boxes, so candies plus equals to ai. Okay, so I've got the total number of candies I can use. I know number of candies used in each box, then I can easily calculate what would if it is possible that I put candies in each box or not. uh, let's see the implementation for this one. Okay, in an, and this is the check function, and this is the binary search function. Binary search on answer, standard binary search 0 to 180 in the constraints. Okay, how I'm checking is, I passed an integer small k, if it is possible to make small k groups. Okay, sum equals to minimum of k comma it. K is the t I was describing the clipboard. Okay, sum by k. I told you we have to divide by k. The number of boxes we can use is greater than equals to k, then we return true, else return false. That's it. um, so let's move on to the final problem, which is a peculiar arrangement. It was an interesting problem, didn't take too much, but it's actually a tricky problem. Okay, so in peculiar arrangement we are given an array of numbers. Okay, an array of numbers. Chef is given an array a of size n, considers to be good if no two adjacent elements are equal, and it has most one local maximum and local minimum. Okay, and there are two operations in which I can change ai to aj. First operation, ai to aj, which cost only 0. Okay, then there is uh, ai to any integer which cost k. Okay, so main is how I use this operation. Let's check how the graphs would become. Okay, so what can the graph look like? This 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 this, or maybe like this. Okay, so we can see all of the graphs are only sub part of these, so we'll technically need to look at what is these are. Okay, so what we can see is every number
every number in this can occurs at most two times, here or here and here or here, if it is either local maxima or local minima. Otherwise it can occur at three different points. Okay, the maximum will occur two times, minimum will occur two times, and the other will occur three times. Okay, plain simple. And there is also an extra condition that no like these maxima okay, it has to be their two adjacent element cannot be equal. Okay, it either has to be strictly increasing graph at point local maxima, local minimum, or strictly decreasing. So once we have got this analysis, we look further into the first operation. Okay, let's say I got an array 1 2 3 4 and 4. Okay, uh, it is stringly increasing. Let's use some duplicates. Okay, 1, let's call it 3, 1, 3 and 2. Can I convert this graph to its permutation? Can I always convert this graph to its permutation? Okay, yes I can. How? I can always shift bits. Okay, okay, since I can make this equals to 1 1 1, this equals to this, anything I can do. So what I can do, I can just make it 1 2 3 and 3 2. Technically I've got what I want, and these are just extra waste bits. I can just change to any of these, whatever, it's not a problem. Okay, so if I want to convert it to a permutation, okay, let's call it 3 2 1 3 2. So what I'll do is I'll just need 3 here, but I'll need to preserve 1. So what I'll do is just put 1 here and choose this 3 to copy from this 3. Okay, 3 2 3 1 2. So then 3 2, then exchange these. Okay, so I'll need to preserve 3, so put 3 here, 1 here. Anyway, I can change to its permutation even if there is one duplicate available. Okay, so now what I have to do is I have to just eliminate the duplicates. Okay, I can take one number thrice. Okay, all other number thrice, maximum 2 times and minimum 2 times. Let n be the number of elements in the array. Okay, so let me erase this. Okay, now I have n elements. I am taking 2 for the maxima, 2 for the minima. Okay, and the rest are 3. Okay, so what if I map all the numbers? Let's say I get k distinct numbers. That is my main aim here. How many distinct numbers I have got? Okay, and how many distinct numbers I do I need to make this possible? Okay, let's it will be the value of distinct minus something by 3 plus 2. Okay, let's how did I calculate it? Two numbers I'm taking for the minima and maxima. Okay, plus four numbers it has created from n, two for the top, two for the bottom, and three I can choose for any numbers. So seal of this will be the answer. Seal, you can say this type bracket. So once we got this formula, it's not much of a problem. There are some edge cases like if there is 1 1 1. Okay, by the formula, uh, technically it is only it needs three distinct. If there is only one, the main edge case comes in n equals to 2. Okay, according to the formula, we would need only one, just the maximum. But since these elements have to be distinct, so we will need twos. There are some basic edge cases for n less than 5. Otherwise, the formula would work. So let's check out my implementation, which should be this. I mapped every number, calculated the number of distinct elements I would need using this formula, n minus 2 by 2. This is just using n minus 4 by 3, but with using seal, just basic maths. And then the edge case, if n equals to 1, distance equals to 1, n between 1 and 4, then distance equals to 2,
Then if I already have more distinct number than required, then 0. Otherwise, the number of distinct number I need minus the distinct number already I have into the cost of the operation. Simple enough. That's it for the video. So everyone, let me know if you want any other contest discussion of either at code or co forces, lead code, whatever. So that's it for the video, and peace out.